Hey, so I wanted to just, because especially of the confusion that we had in class today with the document that I shared with you not being an updated version of the document and having an equation wrong, just to record a quick screencast of going through this activity. You'll want to do this on your own, obviously, but this will go through some of the pieces so that if you get stuck, you can pop to the right location and get a little bit of help. So I'm going to start with the instructions here on the right-hand side of the screen, and Logger Pro is open, and I've inserted my video already so that we can watch this. And the first thing that we need to do is we need to add a point to the center of the car in each frame of the video and set a vertical scale of the window based on the measurements of the roller coaster. And if I scroll up here, the important thing is that the roller coaster car starts at 0.95 meters off the table. And then the height of the top of the loop should be 0.46. So let's do that first. Let's pull open the video analysis tools and we'll set a scale. We'll set a scale. So we'll go from the tabletop to the initial height of the car, which will be up here. And we'll call that 0.96. Let's advance to where the car is up at the top. Yep, that's about the right height. And then let's confirm that distance. So we'll measure a distance here from the top of the loop down to the table just to make sure that we've gotten it correct. 0.42, okay, so pretty close, right? Within a few percent, we're okay there. And now I want to put a point on the screen at each point. I'm actually just going to do a couple of those. And then I'm going to pause the video. Okay, so I've now gone around the full data collection. So we've gone around here and you can see that I've added the points around the video. That takes a couple of minutes. I just didn't want to record it all with the video. As we create that, we get our plot of horizontal and vertical motion that you want to make sure that you can interpret and understand where you see things like how the X position changes as we move. We start off with a positive change in X, for example, as the cart moves to the right, and then we get a quick negative as it moves backwards. Y value goes down, up through the loop, etc. Let's go back to our instructions and see what we need to do next. So one thing you might want to do is you might want to adjust this graph just a little bit so that you don't see the rise at the end. I only collected a few points on that hill. It's so very consistent and constant speed because it's driven by a motor. So I might want to change this that I just go through, like, say, 7 seconds or so, and I see the most relevant part of the motion on this graph. So the next thing I'm going to need to do, and this is where I had made the mistake, is we need to make a new calculated column for the speed of the cart. And to do this, we'll do the vector addition of the x velocity and y velocity. The picture here demonstrates that, and here's the equation. And so we're going to do a new calculated column with the speed, and we're going to do the square root of the x velocity squared plus the y velocity squared. So we'll go to Data, New Calculated Column, and here we're going to call it Speed. We give it a different short name, but speed's pretty short anyway, and meters per second. And so you can either pull from the functions for the square root is written here, or you can just type it in. And to get the data columns, I'm going to grab from here, x velocity caret 2 plus y velocity caret 2. There's my equation. And I'll click Done. So now we have the speed calculated at each point along the graph. And let me just take a look at that. So what does that graph look like? So here with the speed, again, maybe I'll shorten this up to the 7 seconds. So we have the places where the speed gets greater, or smaller, reaches 0 at some point as we move through the motion. So there's my speed. It's a little noisy, not so bad. And it looks about like what the data we would expect was. You're going to want to make sure where those different maxima and minima are for points on the roller coaster as you work through. This next one is a little bit of trouble, especially if you haven't taken calculus, but we just need to enter this integral value so that we can get the distance that the cart has traveled. I'm going to do the same thing with a new calculated column. So we'll go to data, new calculated column. And for this one, I'm going to have distance traveled. Call it dist. We'll give it units of meters. And in this case, I'm just going to type what's there. Integral speed, quote, time. So you can just type that whole thing in. You could probably even paste it in, no problem. Click done. And now we have, now let's take a look at the distance traveled. Okay, so now we have this uniformly increasing value for how far the car has gone. Cut it back to 7 seconds again. And we see that in some places the car is not moving very much. In other places it's moving forward rather quickly. So that should be related, obviously, to the speed graph. And in fact, it might be worth looking at both of those together by using more. And then we'll add the speed graph as well. And we can see that where the speed is large, the slope of this graph is large. And where the speed is low, the slope is low. And where the speed goes to 0, the slope goes to 0. But let's just look at the distance traveled. Okay. The next piece asks us to look at the potential energy due to gravity, the kinetic energy, and the total mechanical energy, given that the mass of the coaster is 0.0602 kilograms. This is what we had done in class. So adding those is going to be fairly easy. It's just going to be an experience of working with those new calculated columns. I'll do them live. So we have, let's do kinetic energy. I-N-E-T-I-C. E-K. And units of joules. And so here we can do 0.5 times 0.0602 times, oh, and we actually have calculated the speed. So we can just do the calculation of speed squared. The potential energy, we'll do a new calculated column. Potential. Okay. We'll do EP, also joules. So we have M, 0.0602 kilograms times 9.8 meters per second squared times the height. So in this case, the height is the Y position. Click done there. And then we'll do one more calculation. So data, new calculated column, mechanical energy, ME joules, and that's going to be the kinetic energy plus the potential energy. Done. So now let's take a look at these on the graph. So we have kinetic energy. And again, let's only go up to 7 seconds. A little bit hard to see because of the color that's been chosen. I could change that in the options if I wanted to. The potential energy. Also just going up to 7 seconds. Okay, follows the height very nicely. And the mechanical energy. This is probably the most interesting one because what we're seeing is we're seeing the mechanical energy gradually disappear. Right? And so when the potential energy plus kinetic energy is disappearing, we know that something interesting is going on there. This is them, we can plot all three of those together versus time. So we can go more. We can look at kinetic, potential, and mechanical versus time. So we can kind of see how the kinetic energy comes up. Oops, why is this not? Well, here's something that's interesting. So in this case, the potential energy never really goes all the way to zero. And part of the reason for that is just based on where the origin was set. I can fix that if I want. I could take, for example, the origin of my graph, and I could make it so that that y-axis, right, lines up so that the potential energy goes to zero in this figure. And you'll see that the kinetic energy doesn't change, and neither really does the total mechanical energy except for an offset. So it's not a big deal, but it does help to line it up a little bit, I guess. So this is we're looking versus time, which is one way of thinking about how these changes take place. But we can also graph this versus the distance traveled. And if we go from 0 to, it looks like, about 4 meters, we have another image here of how this is changing. The reason it's nice to look versus the distance traveled is because here we can think about the change that we have in the mechanical energy as a function of distance, and that's going to make it easier to calculate those forces of friction. Hopefully this is helpful to you, and I will see you in class soon.